Okay, so here we are at part four, and we're going to be looking at spectroscopic techniques today, in particular mass spectrometry. Now, you've looked at mass spectrometry before, and we've done some work on that in AS, but we're going to do some recap first, and then go a little bit further with that into a bit more detail. And you will also be in lesson using mass spectrometry and mass spectroscopy information together to identify unknown compounds. So it's actually not just the reason it's spectroscopic techniques is because you don't just use one, you can use multiple different techniques to get as much information as possible about a compound in order to make an informed decision about what that compound may be. So that's kind of the plan. Now, just a quick note as well, it'd be really useful if you could actually give any sort of feedback to your teachers in lesson about these because I'm making them as we go, so they're not all sort of made in a bank somewhere. They are, adaptable. So it'd be really useful if you could just, it doesn't have to be now, just sort of whenever, just let your teachers know anything that kind of works quite well or anything that's not really working greatly, just in your own opinion. Doesn't matter. I'm not going to take offense to or anything. It's really useful to get feedback about any aspects of this, so that I can actually adapt it as we go, modify it and change them so that they get better. So let's go. Questions as usual. We've just got the three there. We're going to start off with some recap, like I said, and then we will move on to the new stuff. And then we'll do a couple of practice questions as well. So yeah, pause those as usual, have a look at those, see where we're going. Okay, so hopefully this diagram is familiar to you. You've either drawn it yourself before in AS, or you've got a diagram of that. So hopefully you've seen that. And it's showing us a very sort of simplified depiction of what happens in a time of flight mass spectrometer. So the essence of it really is you have a sample inlet. So you have your gaseous sample gets ionized by a bombardment of electrons. It then gets accelerated, and the time is measured that it takes for these ions to get from the acceleration area to the detector. And obviously, the longer it takes them, the heavier they are, the shorter time it takes them, the lighter they are. So first step really, like I said, just to ionize your sample. And then these particles are accelerated with a potential difference. So just a few equations here. You don't need to, memorize these or know these or anything, but it's just a bit of information. So EP, the potential energy, is equal to the charge of the particle, which will most likely be 1 in all these cases, multiplied by the potential difference, so the voltage that you will apply, and that will be constant. Then all of that potential energy is converted into kinetic energy as it starts to move. Okay, so we can say that the potential energy is equal to the kinetic energy, and the kinetic energy is equal to obviously a half mv squared, where m is the mass of that particle. So again, you don't need to memorize or know these, but what you can do if you want to see this, how this actually is proven that that the time is based on the mass and the charge. You can rearrange this equation with velocity is equal to the distance divided by the time that it takes, and you can get an equation for time in terms of charge and mass in our mass spectrometer output. So when we get our graphs, the x-axis is mass to charge ratio. So it's basically like how is the time it takes related to its mass and its charge. So if you want to do that, you can have a little play with those equations and get something in terms of time for mass and charge. And for anyone that's interested, I'll just show you at the end as well, so you can have a look at that. So yeah, what do we actually need to know? Well, we need to know that all the particles receive the same potential energy, okay, from this voltage, and that's then converted completely into kinetic energy. So therefore, they all have the same kinetic energy, and that means that the length of the time that it takes for the ion to reach the detector is proportional to its mass. If it has a high mass, it's going to take longer to get there, okay, because obviously the energy, like we said, is constant, so that doesn't change. So all that can change is the mass and the velocity. So mass goes up, velocity has to go down. Mass goes down, velocity goes up. So that's really the thing. That's the principle behind it. Okay, so that hopefully was just some recap. And now we're going to talk about fragmentation, because this is really the next bit that we're going to be looking at. So these molecular ions are actually energetically not very stable, and they can kind of break apart, okay, into two smaller fragments, yeah, two other pieces. One will have a charge, one will carry that charge, and the other one will be neutral. So only one will be detected. Only things with a charge in this mass spectrometer can actually be detected. So, for example, here, this M plus or whatever it is could split up into A plus and B. B wouldn't be detected whatsoever. Okay, the non-charged particles aren't detected, only the charged ones. So it could either split up into A plus and B, but obviously it could also split up into A and B plus. So you would actually detect both, but you wouldn't detect them from the same splitting. It would be from different splitting there. So we can see a mass spectra graph here, and this is for 2-methyl-butane. Okay, nice and simple. And we've got all these different peaks that are numbered. And all of those peaks are actually, well, apart from one of them, all of those peaks are relating to different fragments of this. Okay, now there are lots of different peaks here, but we're only interested in the ones that are labeled for now. So what I'd like you to do is see if you can assign these numbered peaks to the different fragments of 2-methyl-butane. Now obviously 72, we're familiar with that. That's going to be the M plus, so the molecular iron peak. Yeah, so the peak farthest to the right is going to be the molecular iron peak. Okay, there is some exceptions to that, but for now, the farthest peak to the right, that's going to be basically the peak that shows you the entire molecule without it being split. Whereas all these other ones, 57, 43, 29, those are all going to be present due to smaller fragments being detected. Now, there are some suggested fragment tables in your Chemical Ideas book, so some common fragments on page 143. So you can have a look at those. So what you want to do is just assign those peaks to different sections of this molecule. So pause it here, give it a go. Okay, so hopefully you will have kind of got through that quite quickly. Obviously the molecular iron peak is 72, and we'll go through peaks 1, 2, and 3 now, one by one. So the peak at 57, if you actually do 72 minus 57, you'll work out that the difference is 15. So 15 has been broken off our main molecule. So something that adds up to 15, and that's quite simple. Obviously, it's just a CH3. Yeah, so 12 plus 3 is obviously 15. So a CH3 has been broken off there, which means that it must be basically the normal chain without that side group. Then we've got 43, which is 72 minus 29. So 29 has been lost, which is actually a CH2 and a CH3 group. Okay, so this part has been broken off, leaving us with this. And then finally, the peak at 29 is well, the opposite. It's the CH2, CH3 part. Okay, so it's that bit there. So we have those three peaks which correspond to these three different fragments. Okay, and that's kind of a good way to do it, is just to work out what's been lost. So, you know, take one away from the other, take the peak number away from the M plus peak value, and then work out what's been lost, and then you can go from there. So that's basically that's basically what it is. It's just assigning the different peaks to the likely parts of a molecule, the likely fragments of that. But sometimes you will see some peaks that are difficult to assign, and you've got to really think about all the different possibilities that it could be, even if they seem a bit unlikely. For example, if we do a mass spec here of phenol, 77 is the number that you'd expect for the benzene part. Okay, but you can actually get peaks lower than that. Okay, you can get numbers lower than 77, which seems a bit weird because I mean, yes, you might be able to lose some hydrogens, but if this is a ring structure, you may not expect it to break, when in fact it can. Okay, so this ring can actually break apart and no longer be a ring anymore, which means that you could actually find some peaks that have masses lower than you'd expect. If this ring was to break, it could then fragment further. So just bear that in mind, that rings can actually break in this bombardment of electrons. Okay, so that's that. And so now just looking at some isotopes within compounds. So compounds which only contain hydrogen carbon, you may get an N+1 peak. And what I mean by that is if you have a peak one space to the right of your molecular iron peak. And that could be present to a C13 isotope peak. So obviously some carbon, a very small amount of carbon, is actually carbon 13 in any given sample, about 1%. And so you could get a very, very small carbon 13 isotope peak, just one space to the right of your molecular iron peak. If you have compounds which contain oxygen, you may get an N+2 peak, and that would be due to oxygen 18 being present in a small amount of the sample. And then if you have compounds which contain chlorine, there might also be an N+2 peak due to the chlorine 37 being present. So it's worth looking for these. You may have to identify them. They won't usually be numbered. So most of the peaks will actually be labeled, whereas an isotope peak wouldn't be labeled as such. You just have to look for it and realize that, oh, that must be an isotope peak. So the fragment peaks, yeah, will be numbered with their MZ value, whereas the isotope peaks won't be numbered. Okay, so that's mass spectrometry. We've had a look at IR before, and we've done some stuff with that, and you know how to use your data sheets to do that. And you will actually have to combine both mass spec and IR stuff together to solve problems. So you have to use every bit of information available to you. It doesn't matter too much where you start. It's quite useful to start with IR to see what kind of groups are present, and then think about the structure of that, and then look at the mass spec and see, oh, look at these fragments. Okay, so start building a picture. And bear in mind as well, the absence of peaks is just as important as the presence of them. So knowing what isn't in the compound is just as important as knowing what is, okay? Because you can rule things off. If you have no OH peak in a IR, then you know that you don't have, like an alcohol, carboxylic acid, or anything like that, yeah? So it's just as useful looking for what isn't there as to what is there, okay? So here's a proper practice question. Now the mass spec of penten-1-ol and ethyl ethanoate are shown there, A and B, but we don't know which is which. So what you've got to do is match the correct spectrum, okay, with each of those molecules. And what you'll need to do is assign at least 2 of those fragments, not including the M+ peak. So what I mean by that is you must assign at least 2 of the actual numbers, okay, so 70, 55, 87, 42, 31, 2 of those to the compound, and 2 of these ones to the other compound, okay, to prove basically that you have actually assigned them correctly. So have a look through this. You can pause it here, it might take you a little while, but just look for which one fits best and which one is going to fit to each one. Obviously you'll notice that 88 is present both there, and that's because they are they have the same molecular mass. Sorry, they have the same molecular mass. To make it, obviously, it would be a lot easier if they didn't, because you just look at the molecular ion peak. They have the same molecular mass, so you're basically trying to identify which is which. Okay, so first of all, we'll look at the penten-1-ol. Now, the peak at 87 is actually present to just hydrogen being lost. Yeah, so we've just got one hydrogen being lost, and that's actually the hydrogen, the slightly acidic hydrogen that we get on an alcohol. So there's really nice indication that A is actually our alcohol. Then we have a peak at 70, which is a loss of H2O. Now this one you may not have got, but it is characteristic for alcohols to actually lose H2O, which is obviously 18. So if you see that 18 has been lost, then that usually identifies that it is an alcohol that you're looking at. With the loss of H2O. Then we have the peak at 42, which is just from CH2, 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 and then the peak at 31, which is CH2OH. Okay, so obviously this last bit. Excellent. Okay, so we'll look at the other one. So fragments of B. So here we've got a picture of B here. 73 is actually due to just having a CH3 lost, because obviously CH3 is 15. So that's 73 take away 15. 73 plus 15 gives us 88. Then we've got 45, which is due to this part here, the CH3CH2O, and then we finally have 43, which is due to this whole bit here. So hopefully that wasn't too difficult, and you managed to have a go at that. If you did find it hard, just go back and have a look at those spectra again and see and try and identify these different fragments yourself. Even if you didn't get them the first time, just identify them and see how they were found. And if you're finding these difficult, don't hesitate to have a look in your ideas book at this section and see if you can look at some of the questions in there. They might help you. And you'll get a chance to do some more practice with these, obviously, in lesson as well. Okay, so hopefully these questions are answerable now. So I'll leave that there for a second. You can pause it, see if you can just jot down some answers to those, and we'll go through them. So, what does the M+ peak represent in a mass spectrum, and what does it allow us to calculate? Well, it represents the molecular ion peak, and it can be used to find the molecular formula, okay, of the whole thing. How are different isotopes within compounds identified on a mass spectrum? Well, n+2 peaks for chlorine and oxygen, so a peak two spaces to the right, yeah, of the n plus peak, and an n+1 peak for carbon. What is fragmentation, and how does it allow us to identify groups within a compound? So molecules fragment into smaller units, which can be assigned to particular parts of the compound. So they fragment into smaller ions because they're quite unstable, and these ions can also be detected, and it allows us to assign those to particular groups of the compound. So hopefully that was okay. Wasn't too long, this one. So good luck with that. Bring any questions to class, and any feedback would be greatly appreciated. So yeah, good luck. Okay, so we're just going to have a look at those equations that we spoke about earlier. So we've got potential energy is equal to the charge times the potential difference, and we've also got the kinetic energy is equal to a half mv squared. We said that the potential energy is equal to the kinetic energy. Okay, so all of the potential energy that those particles have is converted to kinetic energy as soon as they start moving. So that allows us to write down the fact that the charge times the potential difference is equal to a half mv squared. Okay. We also know that velocity is the distance that it's going to travel divided by the time that it took. So we can say that all of this distance divided by time squared. And now we just want to do some rearranging. So we can multiply both sides by 2 and divide by m, okay, to get rid of this. So we have 2qu divided by m is equal to this. We want it in terms of time, so it's useful here to inverse both sides so that we get t on the top. So we can do m over 2qu is equal to time divided by distance squared, and then we can square root everything. So we have m over 2qu is equal to time divided by distance, multiply both sides by d for distance, so we get d root m over 2qu, should be root everything, is equal to time. Now obviously the distance is not going to change, the potential difference isn't going to change, so d and u and obviously the 2 we can take out because they're constant, so we can say that d over root 2u is equal to constant k, okay, and therefore we get the fact that time is equal to k root m over q. That should be root everything. So the time is equal to a constant multiplied by the root of mass over charge. So basically, as the mass goes up, the time goes up. As the mass goes down, the time goes down, assuming that the charge is 1. But this also says the fact that we could have different charges. Obviously, a charge of 2 would decrease the time. So the higher the charge, also the lower the time for each mass value. So there's our little equation that shows us that how the time is related to the mass and the charge.